Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Hector, who completed one of our courses that we offer online. It's called ROS2 Basics in 5 days for the Python programming language. And he's going to show us the project that he had to do for the course. So this course is accompanied by a project that you have to do on a real robot that we have here. So he's going to show us the behaviors he programmed for a robot in our lab. And yes, so I'm excited to see it. Welcome, Hector. How are you doing?
Fine, thank you, Rodrigo.
That's great. So yes, like I said, whenever you want, you can start sharing your screen, and then you can start explaining us how you went about your project.
Perfect. So let me share my screen. And this is using your application. No? The construct will give you the capacity in this all-in-one browser screen to connect both to the real robot that you can use, the notes for the course that explain how to perform the operations that are being learned, in this course, and then the console to interact with the system and the code. It's a little bit you have to get used to it because you will have all the information in the single screen. So you have to be moving and jumping around. In this case, we have the connection to the real robot. I guess this is in your installations. I don't know where this is.
Yes, this is in our offices.
So I don't know where it is, but I can control it from the north of Spain today. And we have this joystick, and this is provided by the construct, in which I can locate the robot in the correct position to start. I will explain the limitations of the project. That's why I'm going to locate it in a suitable position, because the robot is supposed to locate the wall that is closest to it when it starts. And then the robot should follow the wall at a distance of around 30 centimeters to the wall. Okay, it has to complete the track. It's more or less, it corresponds to following the center line, the dash lines in the track. Okay, so that's what it's supposed to do. First of all, it will have to locate the wall, get to the correct distance to the wall, then align itself, leaving the wall at the right, complete or follow the wall, and complete a single lap. When it completes the lap, it should report the position points it has gone through. And I have added, I've made the robot stop just to check when exactly it arrives to the point. It may work or it may not. There is a little bit of error in the position of the robot. So depending on where you place it and the obstacles, may not be completely capable of stopping exactly at the starting position. Okay, but it usually should do it close to that. Let me move around the robot a little bit. A bit in there, so we can see that it should rotate in this case, to the right. This will be the closest wall. One limitation that I have is I could not discriminate between obstacles and walls. If I place a robot closer to these obstacles we have on the track, it will think it's a wall and will try to follow it. Okay, so we have to make sure that it is closer to the wall than the obstacle. If it doesn't work, we'll relocate the robot to a closer position. So when we have this done, what I will do is I will launch the main node that controls the robot, with ROS2 launch. The name of the module that enables this behavior is wall follower, and the file that contains. Sorry. Let me see if I can. There you go. The file that contains. Let me clear this. Okay. I don't know why. So ROS2 launch. The name is wall follower. It's our module. Main.launch.py. Okay. This file resides here in the launch folder of the wall follower package, main.launch.py. This is the file that will launch the 3 nodes that we need to launch to simulate this behavior. One node, the wall finder, will find the wall follower will follow the wall, and the odometry recorder will tell us where the robot is while it's following the track. So it should work. If I launch this, if everything goes fine, the robot should start rotating.
There it goes.
Yeah, it will go slowly. I have limited the velocity because there are some limitations to real-time robots, and it's better to do it first slow. You have a limitation. No, I cannot push the robot as fast.
Especially that's just for the cable, because I mean, they're pretty heavy wheels, but sometimes the cable, it yanks it too strongly, and that will create an issue. So I'm glad you did that.
So the robot located the wall, decided that it's in the correct position, aligns itself to the right, and then follows the wall. When it arrives close to a frontal wall, it will increase the rotational speed. It will enter in a banking mode to avoid the wall. The walls are not symmetrically located, so from time to time, each of the turns against the wall dislocates it from the center part of the track. So we say that it's trying to follow at 30 centimeters. It will go from a minimum distance of 0.25 meters to 0.35 meters. It's not proportional on anything. It's a very simple control system. I'm not trying to maintain exactly constantly the center line. Made the project a little bit too complex, for the idea of learning the basics of ROS. So ideally, when it reaches the initial point, it should stop. We missed the point. We didn't miss the point. I have added a little bit of, let's say, leeway, a little bit of tolerance, because the main reason is the frontal walls will make it turn too fast sometimes, so it will move around. It has to end. Usually it ends 10 centimeters, 5 to 10 centimeters from the starting point. We should be able to see that. So we had this running because there's no point on looking at this. Now this is constantly communicating that it's stopping. What I have done is, as soon as I have completed a full track, I will send it into a stop mode. It has so let me stop it for a while. I think we miss it because there is a limit to the logging we can have. Maybe I should have maybe. And there will be. There you go. So this logging, the logging I have added, because this is a learning experience, and sometimes I was confused on what the robot is doing. Whenever it changes behavior, it will send you a message. There has to be a point in which, when we finish the complete lap, because this is reporting the action, what it is doing, and the distance, how far we have moved from the odometry of the robot itself, and how far we are from the initial point, the X and the Y. So we are 23 centimeters away in the X direction and 0.03 meters away in the Y direction. There is a point when we
initial position, you said?
From the initial position, correct. When we complete a lap, the odometry will give you all the points we have gone through. Which is this, which is a requirement of the project. This is an action in ROS2 that when it's completed, the final step in the action is to provide all the points we have covered in this lap. So to do this, I will not start with the main behavior. The main behavior is the wall following. The robot, let's say the cruise condition for this robot is to follow the wall. That will be the main, let's say, the central behavior. So it makes sense to organize the rest of the services and actions around that main behavior. I think it's interesting to see first how it will locate the wall, which is the first step it will take. So to look at that inside our launch, in our wall follower module, we will have the wall follower code, which is inside, and here we'll have the three. Let me make this. There you go. We'll have the three nodes, the finder, the follower, and the recorder. The finder is a node that generates a service server. When the main node calls or asks, will act as a client for the wall finder service, will create, the important part is here, will create a service call, and this node will have both a publisher and subscriber. It will publish, as this wall finding node has to have the capacity to translate the robot into the position that is close to the wall, we'll have a publisher into the twist message, a message that is of the type twist that commands the velocity of the robot. So it will tell the robot how fast to move, and to locate how far the wall is, it's subscribed to the scan topic, which is of the type laser scan, and this is giving you an array with, I think, 720 points all around the laser sensor of the robot, telling you what is the distance to each of those points. Okay.
Yes.
Here, the important thing is we need to parallelize this activity. Whatever of these three activities will be a blocking activity for the processor. So we need to generate two different groups of processes, no? G1 and G2, so that no process blocks the operation of the other one, no? So we generate two callback groups, G1 and G2, and we will see this below in the main launching of the node, that we execute them with a multi-threaded executor with two threads. So we'll have two separate activities going together, because otherwise they will get no. The functioning is relatively, I have some comments of things I couldn't do. I will explain that. The behavior is relatively simple. The subscriber will receive information from the laser scan, and we will use that to set both the the distance to the right of the robot and the distance to the front of the robot, corresponding to the 360 entry in the range and the 180 in the range. Sometimes this is frustrating because you have to know every laser sensor is different, or is reporting their position differently. You don't know if the 0 element is the front, the right, the left, or the back. So you have to do a little bit of hacking by moving the robot around. Yes. You don't have access to the full specification to know what it is. With a little bit of tampering, at the end you will get what number of the range belongs to each point of the robot. No, we will get the minimum. We will define the motion of the motion message for the robot. And while we are doing this, I have several short sleeps. I am using a constant value for a short sleep to give time to the sensor of the robot to actually provide the first readings. In the simulation is perfect, and the robot will work immediately. As soon as you start it, you will start receiving laser ranges. In reality, if you start the nodes, the first value that you will receive will be probably the first few cycles of the message will be full of not availables or zeros, and can result in wrong behavior. So reality requires adapting to small delays that the hardware by necessity has. No, so we generate a short sleep, and then we start doing our work. What we will do here is find the difference in the distance, the minimum distance to the distance to the right, and we have to make that smaller than 0.2 to have a precision. If you try to make everything equal, if you try to make that the distance that the robot is reading to the right is actually the minimum distance, the precision of that laser is very high. I think you have 8 decimal places. So it's very difficult to hit it. So this is introducing a small precision into it. No? So I'm saying here that the robot will be fine looking at the wall if the distance to the wall is more or less 2 centimeters. No, it's not exactly the position, but you will be doing. Then it will find the wall. It will rotate, selecting to the left or to the right, depending where the wall is. It will rotate positively or negatively to the left or to the right, and then as soon as it has found the wall, it will try to locate the front position of the laser to make it 30 centimeters. No, so if it's very close to the wall, it comes back. If it's too far, it will get close to the wall. And in that position, we'll have the correct situation, and we will align ourselves to the right. When we are aligned to the right, we have finished our process, and we are in the starting position to start our work following behavior. All this chunk that I couldn't complete here, I was trying to discriminate a wall from an obstacle, because I couldn't find any ready-made algorithm to discriminate this. So I'm thinking that maybe the standard deviation of the distances will give you, because it's very obvious in the laser scan what is a wall and what is an obstacle. But I didn't have anything to really discriminate those small obstacles in the center of the track. So it's a limitation. It has to be close to the wall to really select the wall. If it's closer to the obstacle, it will lock onto the obstacle and try to follow that. Okay.
Right.
So this wall finder leaves us at the wall, and then the wall following behavior will start. Okay. This is the main node. In this main node, we define the requirements we need. Know that the maximum distance to the wall is 0.3, the minimum distance 0.2. If we adjust this, we get a more jerky movement of the robot, but it will stay always in the middle. Okay, this is not proportional. No, what I'm doing here is, if the distance is very high, turn to the wall, and if it's very low, turn against the wall, and always in a constant way. A way to improve this is, if you are very far from the wall, rotate very fast. If you are almost in the center line, rotate very slow. Right. So we will get a smoother wall following behavior. In any case, this one we have seen works acceptably good. No, the wall follower by itself, the only thing it needs to follow the wall is to subscribe to the laser. So it has to know what is the distance to the obstacles, and will publish to the velocity topic. No, the same behavior as the wall finder. Right. What we need in this behavior, and this is the main node, no, the node that will control everything, we'll have to launch the client. So this is the part that will ask the service node to locate the wall. We will wait for a response from this server, and as soon as we have that response and that process is finished, we will start the wall behavior, and also we will start the action server for the odometry, the part that is going to start counting our distance and will tell us that we have completed a full lap. Send goal and goal response and result and so on. This is what will happen when the odometry action is finished. When the odometer has completed its action, we will handle the response with these functions. As we have seen, it has stopped. No, usually it doesn't. The trick for that, or the only thing I'm doing, is the response from the odometer node sets a Boolean variable here, one lap, to true. And if this is true, the only message that the action will take, the robot, the only action it will take will be to stop. When is the robot taking the actions? The take action element that will control the behavior of the robot comes from the laser callback. So we are subscribed to the laser. Whenever we receive a message from the laser, we will update the distance to the laser regions, and we will tell the robot to take any action. So we have the take action function. And here we have all the possible actions. If we are very close to we are far from the wall, turn right into the wall. If we are close to the wall, turn left to the wall. All these, turn right and turn left, are functions that will generate a twist message that will set the corresponding linear speed or rotational speed. Not to modify them a lot, linear speed and rotational speed are these constants up here. If we modify this, we can make a robot more faster or slower, without risking it too much away from the center line. And in this case, there are no. It's not a very, from the point of view of threads, it's not a very complex node. So we have a single thread going on, which is the thread that is controlling the message received from the sensor laser topic and sending messages to the command velocity topic, which is moving the robot. Okay, so this is the main one, and the final one is the odometry recorder, and this one is an action node. The action is a request is like a server, but you can request it, and it will be you can cancel it. Potentially, you will cancel it midway, and periodically will be sending you updates on the situation of the action you have requested. In this case, the action is just start recording the distance you cover, and as soon as you are at the same point as you started, send us a message. This is not stopping the robot. The robot is being stopped by the main one follower, which, if the response from the odometry node is that you are already a lap down, it will lock the robot in the stop. position and it will not move. The odometry logger needs to subscribe to the odometry itself. Is the only thing you need. You are not controlling. This node is not controlling any velocity or is not reading the laser either, and is generating this action server. So this will act as the server. I have some info logging ABC just to check where problems could be. We initialize everything. Distance has to be 0 because potentially I could restart, or tell the robot to stop for a few seconds and then continue again recording a new lap, and we can reset the odometry by making this 0 again. And what this is doing is basically reading the odometry message, looking at the X and Y mainly. Okay, we also have the orientation, we have the angle, rotational angle of the robot, but we are looking at the X and Y positions for the robot and accounting for how much is that distance. Okay, this is basically Euclidean distance, the square root of X squared plus Y squared, and that will tell me the linear distance. The difference between the current position and the other one will be the distance I am away from the starting point. Naturally, that will start increasing as I move in X and Y. As I'm going back again and closing the second point of the lap, the distance will start decreasing, and the X and the Y, the delta in Y and delta in X, will become smaller. When they are between 0 12, so I have a 12 centimeter precision, I could reduce it, okay, and check. So the robot will stop within 12 centimeters of the starting position. I can reduce this, or we could try to reduce this and see if our movement is so precise as to stop it exactly where it started. When it's finished, it just sends the succeed message of the action. So we have a successful action result for this action, and that will cause on the main node the robot to be locked in a stop position, because that's all we have to do. In this case, this node also requires two things to happen at parallel. We need to be reading the odometry and calculating the position. So we are using another multi-threaded execution, and we have two groups of reentrant callbacks to let them take over the processor whenever is required. Okay, so this is basically how it works. What we have done also, or we need to do to complete the project, is we have some custom messages here for the action. We have to define the odometry recorded action, which takes no input. As a feedback, provides current total, and when it's finished, gives us that list of points we have seen in the final report of the lab completion and the wall finder service. And later, that takes also no input and returns the true or false. When it returns true, not true or false, it will return true if a wall has been found. If there are no walls, it will keep on. The poor robot will try to find the wall forever. Okay, there is no timeout, or it's very the behavior is quite simple, and it fits the behavior intended for this project.
This is all. Is that your whole project?
Yes.
All right. Well, congratulations. Really clear explanation.
Thank you, Rodrigo.
Really clear. Do you mind stopping sharing your screen so I can ask you some questions?
Yes.
We don't really need to take a look at the code anymore. All right, great. Yeah, so congratulations. It's really clear, really well explained. And like you said, sometimes the simplest way is the best.
Yes.
Of course, you could complicate your life a million times with different things, but this is a basics course, and this is what we're expecting from a basics course. So congratulations again. I really liked that you attempted to do some extra steps. For example, that obstacle recognizer using the standard deviation. That I think that's really clever.
I don't know. We'll have to look for some algorithms. I'm sure there are, but we'll have to find a way. The problem is, Rodrigo, when you are testing it in the simulator, if you don't take that into account, you will strangely see the robot going to the obstacle. I was thinking, why is it going to? And then you check that effectively the obstacle is the closest thing to the robot.
Right,
Even if you try to locate it in the middle, if you place it too close to the wall, it's like you are cheating. No, the wall is in there.
right.
So ideally, in an advanced course, we could develop the discriminate the obstacle from the wall.
Yeah,
Because it's needed in robotics. No, you have to do it sooner or
right.
later.
So some people have used different types of filters, and for example, what I do for this particular case, in which I only have a lidar, and I actually have done it for example, self-charging, is that I check the width, like say how many continuous readings you have.
Correct.
I mean, this is also, it's it's not
Correct.
completely a solution.
Yes, yes.
I check like, I don't know, like 50 to the right and then 50 to the left. And if there isn't a big, I call it like big reading jumps, let's say like,
yes, a gap.
From 10 centimeters to 1 meter, if there's one of those in that area, you can tell like, all right, that's an obstacle, right? Because I'm expecting it to not deviate that much. And you can translate this to, for example, a shape of an obstacle that you can use, for example, to detect things like a charger or things like that.
Yeah, that's it. In this case, the obstacles you have in your track are triangles, most of them. So they should be trigonometrically is very easy, because if you know the distance to the wall, as you are following a circular path, if it's a straight wall that is perpendicular to your beam, the distance will be the sine of that angle at each point. So you will even be able to detect so a LiDAR is a very powerful sensor to have. Will give you.
I think it's the go-to for.
At the same time, it's very difficult to program for. No, it has this difficulty. No, you have an array of 720 points, floating point with a very high precision. If you don't filter it in some way, or you don't discriminate, because in my project I have truncated all the readings but the centimeter. So I have a centimeter precision in the reading. You could have a millimeter, you can have a micron. I don't know the specification of that sensor, but you can have a very high precision.
Yeah, these are precise. I don't know how much either, but
I don't know. It's very high precision.
You can do millimeters, and I think that's enough for this type of application.
Yes.
And I mean, a lot of the questions I had, you answered for me in your explanation. For example, but I do have one that you talk about how to make it stop, and you talk about this, I think it was 17 centimeter, or something like that, 10 centimeters.
It's at 12.
Okay, and how do you stop this from stopping right away? Right?
Because what I have is a little trick. What I have is, and the distance covered has to be greater than 20 centimeters.
Okay, that's what
everything is a trick. There can be, we'll have to look for other ways. The more we increase the intelligence of the robot, the more coding we'll have to do, unless we have a very advanced system. In this case, I said, okay, as the distance will be 12, I will make it 20. As soon as you have covered 20, I start recording it, and that will. So it's a little bit, this is the reality, and that's why the simulation, because I did all these things in your simulation. You have first the simulation with everything, but the simulation is very clean. Everything is answered immediately.
Right.
And if you can avoid that in the simulation, you tell it to move 1 Armstrong, the computer will tell you that the robot has moved 1 Armstrong, and you have no way. The odometer has no way of locating that. So in the simulation, you can do without any precision. And that will be what will take you, while you jump from the simulation to the real robot, you have to take into account this. There will be delays in time, and there will be delays or error in your reading. And that's the point in which reality comes into play, and you have to modify your code. In this case, my simulation did not look like the real robot code. I had to do quite a bit of work, because one of the main errors is the simulation was working because it was immediately receiving the laser scan sensor. In reality, you'll have a lack of a few milliseconds, and that will be enough to have 3 readings of 0. And the robot will tell you that it has found the wall.
Right. Because it's, of course, I see. I was going to ask you that why does that prevent you from? I see why, because the
That's
servers are
it.
more
So you have to you do this way, or you can increase the precision of the sensor and have a very expensive sensor, or accept that this is your precision for your system, this is your delay, and this is your precision, and program or create your code with those specifications in mind.
right,
So I know
right.
the sensor is
This,
not precise, so I have to do this in this manner. And then if you really need it because your robot is an operating robot, no? You need a very high precision. You need to increase the cost of everything. Everything has
right.
to be more precise. So it depends. Code and hardware will have to go hand in hand with the mission of your robot.
I'm really glad you talk about this because this is exactly what we sort of try to offer with these projects
Yes,
with the
yeah.
real robot.
Yeah, it's very good
Because
because you see completely the process from
right, yes,
coding to reality, and then you will find the real problems with the control.
yes, and if there is a not a complaint but a point of improvement I have on the open source nature of
Yeah,
ROS is that, for example, I mean, there's tons of great tools available for you can just look it up on GitHub and there's a lot of packages,
yes,
but a lot of times they just do it with the simulation and then you find out that when you jump to the
yes,
real robot there'll be a million different things, especially
correct,
for example with the ROS2 and networking, things like little things like that that keep adding up that will
yeah,
change not the logic of your code because at the end of the day you're doing the same things,
correct.
but like how to handle these real
Correct. The
situations.
real behavior, I mean, everything you take from open source code, GitHub, will be 90% useful and correct,
Hmm.
even 92% correct. That 5%, 8% will be dealing with the hardware. What will happen? That no one has the same hardware.
Exactly.
Everyone has different equipment. Then the challenge for open source robotics is, can there be a standard for the hardware itself, precisions, and so on? We are still far from that. But it's something that will be needed finally, because the idea is I have this sensor, because if you take your robot and you replace it with a new LiDAR,
You have to find a
every code,
driver. Yeah, yeah.
every different driver, the front is 0, the front is 90, the refresh rate of the reading is different.
Mm-hmm.
So those are the things that could be improved in the future, but that's a very, I mean, the industry, robotics industry, is not new, but it's not mature by any means. Okay, it's highly mature in the elements I worked before, which is welding robots, which is where everything comes from. But the welding robot is a very specific robot,
Mm-hmm.
very very expensive and so on. Now, with this revolution in robotics, the problem is that is you cannot do everything in a single way. If every robot is the same robot, that's fine. But now we are seeing robots for everything.
Mm-hmm.
Operating room robots, drones, boats. We need to, or this system is the way to go. No, an open operating system and getting a standard
I agree.
process for communication, which is very common. So this is a very powerful tool, of course, for robotics.
Yeah, and yeah, I mean, other than that, I have no other questions except
Yeah.
for uh, curiosity. Um, for example, I see that you, for example, you have a shutdown instruction for your wall follower node at the end,
Yeah.
but then you leave the action server running, and that's why we saw the
Yes.
stopping. Is there
Yes.
a reason for that, or is that
No.
just like you're
No.
testing?
No, I was testing. I wanted it to stop, and I didn't have the. I mean, I stopped doing this. I didn't have the time to stop the servers.
Okay, okay, that's fine. That's
The robot keeps on going, and it becomes locked in the stop position.
mm-hmm.
What I was thinking is put there a timer, wait 15 seconds, reset the robot, another lap,
Yeah,
something
that
like
could
that.
be.
No, keep the robot. This is beyond the requirement of the project. The
Absolutely,
project only was
yes,
asking to report the position, but it
yes.
was very difficult to see if you exactly has the robot went through the starting point.
Right, right, right,
So
right.
I stopped it to see, okay, if we could, you could put a target on the track, put the robot in there,
Mm-hmm.
and see how precisely it stops on target.
Right, right. That's a good idea.
It's no reason at all.
All right. Well, I have no other questions. So, Hector, congratulations again.
Thank
Really,
you.
really nice project. Really clear. And
Yeah.
to everyone else that's watching, you can do what Hector did here in the course. Then the last step to obtain one of our certificates is to come and present and show your work, and that's what we consider, that you actually took something away from our course. So we encourage everyone to take our course and our project. And again, Hector, congratulations, and
Thank
I
you.
hope you learned and took something
Yes,
out.
yes, of course. Yes.
All right, guys. So that's it from us, you guys. So we'll see you guys for our next presentation. And that's it for us, guys. Thank you very much, Hector.
Thanks to you. Goodbye.
Bye-bye. Okay.